Number 2, just like all these problems, the first step is to draw all the forces. This one's a little bit different because instead of trying to get all the forces in either the x or y dimension, I'm going to be getting everything into the parallel or perpendicular dimensions. So parallel dimension would be like this or this. This is all the dimension, this is the dimension in which everything's going to be sliding. And I'm calling it parallel to the slope because this moves up and down parallel to the slope. The pulley changes the direction of this. This is moving up and down, but still. This is all part of the parallel dimension in my thinking. Then there's the perpendicular dimension, which only applies to things going directly out of the hill or directly into the hill. So the beginning forces that I have this weight, 5 times 9.8, and then I have this weight, 6 times 9.8. This is parallel to the hill, so that's fine, I can leave that, but this is pretty useless. So I have to resolve this into a perpendicular vector and a parallel vector. So I draw my weight, that arrow represents the weight, this arrow represents the perpendicular component of the weight, and this arrow represents the parallel component of the weight. So the perpendicular component and the parallel component add up head to tail to give me the actual weight. And the weight itself is just going to go away. I'm trading it for these two. So to find this perpendicular component, if this angle is 40, then this angle is also 40. And if this angle is 40, then I can say that cosine of 40 degrees equals the adjacent over hypotenuse, and therefore the cosine of 40 degrees times the hypotenuse gives me the adjacent. So the perpendicular component is cosine 40 times the weight. And this is the opposite, so I would use sine here. Opposite and hypotenuse are related to one another through sine. So this equals sine 40 times the weight. And when I multiply those out, I get 45 for the perpendicular component, 37.8 for the parallel component. I'm on my way. But there's friction. It's kind of hard to tell what that says. I don't know what that is. Well, I'll be able to, it's probably 0.1. I can figure it out somewhere. Yeah, so here I have friction equals mu times the normal force, and I've got a normal force of 45. So what times 45 would give me 4.5? That must be 0.1. Let's get rid of that. All right, so there are more forces. There's going to be friction. I'll get to that in a minute. But there's also the normal force. And the normal force is perpendicular out of this surface. Now you can count on the fact in this problem that this block is not going to fly out into the air. It's not going to go into the hill. So in this dimension, the net force is 0, which means this force and this force are balanced. So whatever my perpendicular weight component is, that is going to be the normal force too. The only difference is this is directed into the hill, this is directed out. So now that I have this, I can use this to find the force of friction. But before I draw friction, I need to think about which way the friction is going to go. And to think about that, I need to think about the weight of this, and I need to think about the parallel component of the 6 kilogram object's weight. Because these are really playing tug of war with one another. This is the weight pulling it downhill, pulling everything downhill and lifting this up. This is the weight pulling this down and this uphill. And that is heavier than this. So everything's going to move in a clockwise direction here, what I've labeled as a positive direction. And that means friction is going to be downhill. And now I see why I crossed this out. This isn't a very big difference. So if there's a lot of friction on this, the whole thing's not going to move. So probably it didn't move and I had to change the problem to make it move. So I've got all my forces. Oh, well, need to get back to friction. So I know the friction's in this direction because everything's going to move uphill if it moves at all. And the force of friction equals mu, 0.1, times the normal force, 45. So that's 0.45. So I have friction this way. I have this weight pulling here, parallel component of this weight going downhill. These two cancel, but they're there. All right, so now I'll start writing some equations for net force. This is the equation for the entire system. That's useful for finding the acceleration of the whole system. So the net force of the whole system is all the forces added up. I'm considering anything either uphill or down over here to be positive. It's kind of weird, but that's the way it is. So I'm going to say this is a positive force because it's pulling things this way. So positive 49. And then negative 37.8, that's this force. That's the downhill force of the weight of this. Minus 4.5, that's friction. Friction is also acting downhill. And that's it. Those are the only three non-canceling forces. Everything else cancels out. So those add up to 6.7 newtons. So there's still a net force moving this way. This thing is still going to go. The net force equals mass times acceleration. The mass of the whole system is 5 plus 6, 11. So 11 times A equals 6.7. Therefore, A is 0.61 meters per second squared clockwise. So now I know the acceleration. The last part, to find T, I just isolate this. You can do it another way, but this is the easiest way. Just isolate this. This is like what we did in on the last test. And write equations for net force for this 5 kilogram mass. So the net force, based on the sum of the forces, is the tension pulling upward, so that's positive, minus the weight going down, that's negative. The other way to write the net force is to multiply this mass times its acceleration. And I've written 5 times negative 0.61. Because if I'm going to call this a positive t, and this is accelerating downward, then that needs to be a negative acceleration. Now, earlier on, when I was looking at the entire system, I was calling this positive. But now I'm just looking at this, and it makes more sense to call downward negative. And since this is going downward, its acceleration is negative. So 5 times negative 0.61 is the net force. And the net force equals t minus 49, so therefore t has to be 46.